Imagine opening a book that has survived for more than 3,000 years. Its pages, or rather its verses, were memorized long before paper became common. They were passed from teacher to student across countless generations, surviving wars, kingdoms, invasions, and the rise and fall of civilizations. Now, imagine discovering that hidden within one of those ancient traditions is a number that appears astonishingly close to one of the most fundamental constants in modern physics, the speed of light. Coincidence? An overlooked scientific insight, or simply a modern interpretation of an ancient poetic verse? Tonight, we're going to investigate one of the most controversial claims ever made about the Vedas, not with blind belief, not with automatic skepticism, but by following the evidence wherever it leads. Because this story isn't just about numbers. It's about history. It's about language. It's about astronomy. It's about how ancient civilizations understood the universe. And perhaps most importantly, it's about whether we've underestimated what our ancestors were capable of observing. By the end of this journey, you'll understand why millions of people believe the Vedas contained knowledge far ahead of their time, why many historians strongly disagree, what a 14th century Sanskrit scholar named Sāyaṇa actually wrote, how a mysterious number became linked with the speed of light, whether the mathematics really works, and why this debate refuses to disappear even after decades of scholarly discussion. The answer may surprise you, but before we examine the famous verse, before we calculate the mysterious number, before we compare it with modern physics, we need to understand something far more important. What exactly are the Vedas? Because if we misunderstand what these texts are, we'll misunderstand everything that follows. Today, most people know the Vedas only by name. Some think they are simply religious scriptures. Others believe they contain secret scientific knowledge. Still others dismiss them as mythology. The truth is far more fascinating. The Vedas are among humanity's oldest surviving literary traditions. For centuries, they weren't written down at all. Instead, they were preserved entirely through oral transmission. Teachers trained students to memorize every syllable with astonishing precision. Special recitation methods were developed so that even if someone made a mistake, it could be detected and corrected. Modern researchers have often remarked on the extraordinary accuracy of this oral tradition. Whether one approaches the Vedas as sacred literature, historical documents, or cultural treasures, their preservation is one of the greatest intellectual achievements of the ancient world. Within these texts are hymns to nature, reflections on existence, philosophical questions, descriptions of rituals, astronomical observations, poetic metaphors, and verses that continue to puzzle scholars even today. One of those verses, Rig Veda 1.50, is at the center of our story. Interestingly, the verse itself does not explicitly state the speed of light. The connection comes centuries later. Nearly 2,000 years after the earliest composition of the Rig Veda, a scholar named Sāyaṇa wrote an influential commentary explaining many of its verses. Hidden inside that commentary appears a remarkable statement involving the sun and an enormous numerical value. Over the years, some researchers noticed something extraordinary. When the traditional units in Sāyaṇa's statement are converted into modern measurements, the resulting speed is strikingly close to the modern measured speed of light. Close enough to make people stop and ask, how could this be? Was it deliberate? Was it symbolic? Was it describing something entirely different? Or are we forcing modern science onto an ancient text? These questions have divided scholars, scientists, historians, Sanskrit experts, and enthusiasts for decades. Some call it one of the greatest forgotten discoveries in history. Others argue it is nothing more than an accidental numerical coincidence, and that's exactly why this topic deserves careful examination. In today's world, extraordinary claims spread faster than careful research. A single image on social media can convince millions. A short video can turn a complex historical debate into a simple headline. The Vedas knew the speed of light, but history is rarely that simple. Real discoveries require patience. They require context. They require understanding the language, the culture, and the people who produced these texts. Otherwise, we risk misunderstanding both ancient wisdom and modern science. Throughout this documentary, we'll examine original Sanskrit passages. We'll explore how traditional Indian units like the yojana and nimeṣa were understood. We'll perform the calculations ourselves. We'll compare the ancient number with the modern value measured using today's instruments. We'll also hear the strongest arguments from both sides of the debate, because truth doesn't become stronger by ignoring criticism. It becomes stronger by surviving it. Along the way, we'll discover that ancient India made extraordinary contributions to mathematics, astronomy, linguistics, and philosophy. Some are universally accepted, others remain fiercely debated. Understanding the difference is essential. Whether this famous number ultimately represents an astonishing insight or an intriguing coincidence, the investigation itself reveals something remarkable about human curiosity across the centuries. Think about it. Thousands of years ago, people looked at the same sunrise we see today. They watched the stars, they tracked eclipses, they measured shadows, they wondered about time, distance, motion, and the nature of reality. Without telescopes, without lasers, without computers. Yet they asked questions that continue to inspire scientists even now. Perhaps that is the greatest lesson hidden within these ancient texts. Not that they necessarily contained every answer, but that they encouraged humanity to keep asking better questions. And sometimes the questions themselves change history. So, what exactly did Sāyaṇa write? Where did this mysterious number come from? Why do its traditional units matter? And how close is it really to the modern speed of light? In the next chapter, we'll travel back through centuries of history to meet the scholar whose commentary transformed an ancient hymn into one of the most debated scientific mysteries in the world. To understand how an ancient Vedic hymn became linked to one of the most important constants in modern physics, we must first travel nearly 700 years into the past. Not to the time when the Rig Veda was first composed, but to medieval India. The year is the 14th century. Across much of the Indian subcontinent, kingdoms are rising and falling. Great temples, universities, and centers of learning preserve traditions that have already existed for centuries. Sanskrit remains the language of scholarship, philosophy, ritual, and commentary. Learned scholars dedicate their entire lives to understanding texts that are already ancient by their own time. Among these scholars stands one name that would become central to our story: Sāyaṇa. He was not the author of the Rig Veda. He did not claim to have received new revelations. Instead, his life's work was something equally extraordinary: explaining the Vedas. Sāyaṇa served in the court of the Vijayanagara Empire, one of the most influential kingdoms in medieval India. Along with the support of rulers and fellow scholars, he produced extensive commentaries on nearly all four Vedas. These commentaries were not casual notes scribbled in the margins. They were comprehensive explanations of grammar, ritual, symbolism, and traditional interpretations that had been preserved over generations. For historians today, Sāyaṇa's writings are invaluable. Without commentators like him, many ancient Sanskrit expressions would be far more difficult to understand. His work became one of the standard references for students, priests, linguists, and scholars studying the Vedas. Yet hidden within one passage of his commentary lies a sentence that has fueled endless debates in the modern world. A sentence that, on its surface, seems simple, but when examined closely, raises astonishing questions. The passage appears in Sāyaṇa's commentary on Rig Veda 1.50, a hymn praising the sun. The hymn itself celebrates the sun as the bringer of light, life, and order. Like much of Vedic poetry, it combines observation with symbolism, expressing profound ideas through rich imagery. While explaining one of the verses, Sāyaṇa includes a traditional statement that has been translated approximately as, "It is remembered that the sun traverses 2,202 yojanas in half a nimeṣa." That single sentence has become the center of one of the greatest historical controversies surrounding ancient science. At first glance, it doesn't seem remarkable. Ancient cultures often described celestial motions using their own systems of measurement. The Greeks did, the Babylonians did, the Chinese did, Indian astronomers did as well. So why has this particular statement attracted so much attention? The answer lies in two unfamiliar words, yojana and nimeṣa. These are traditional Sanskrit units. A yojana is generally understood as a unit of distance. A nimeṣa is traditionally described as a very small unit of time, often associated in later texts with the blink of an eye. However, there is an important complication. Neither of these units had one universally fixed value throughout Indian history. Different texts, different regions, and different historical periods sometimes used different definitions. This detail is crucial, because the modern claim depends entirely on which values are assigned to these ancient units. If different values are chosen, the final calculation changes dramatically. This is one of the primary reasons historians urge caution before drawing sweeping conclusions. Yet despite these uncertainties, many researchers noticed something extraordinary. Using one commonly cited traditional conversion, the figure attributed to Sāyaṇa converts to a speed astonishingly close to the modern measured speed of light, close enough that it immediately captures the imagination. Could medieval scholars have preserved knowledge far older than themselves? Was Sāyaṇa recording an ancient astronomical tradition? Or is the apparent match simply the result of selecting convenient unit conversions? These questions remain hotly debated. What's often overlooked, however, is that Sāyaṇa himself does not explain this statement as a scientific measurement of light. He introduces it as something remembered in tradition. The Sanskrit wording suggests he is citing an established saying rather than presenting an original calculation of his own. That distinction matters. It means the statement could reflect an older tradition whose exact origin is uncertain, or it could simply be a conventional expression used in the scholarly culture of the time. Modern researchers continue to discuss what, precisely, the statement was intended to describe. Another important question often gets ignored. When Sāyaṇa mentions the sun travelling this immense distance in an incredibly short interval, is he speaking literally, or is he referring to the apparent motion of sunlight? Could the statement be symbolic, poetic, astronomical, or connected to ritual cosmology? The text itself does not explicitly answer these questions. That silence leaves room for interpretation. And where interpretation exists, disagreement naturally follows. Some readers approach the passage convinced that it encodes advanced scientific knowledge. Others argue that interpreting it as the speed of light imposes a modern concept onto a medieval commentary. Both sides appeal to evidence. Both believe they are reading the text correctly. This is precisely why the debate continues. But regardless of where one stands, there is something undeniably fascinating about the survival of this statement. Think about the chain of preservation. An ancient Vedic hymn is transmitted orally for centuries. A medieval scholar writes an influential commentary. That commentary survives through manuscripts. Centuries later, modern scholars translate it. Researchers compare its numerical value with modern physics. And suddenly, a sentence written hundreds of years ago becomes the subject of worldwide discussion. History often works in unexpected ways. Sometimes the smallest line in an old manuscript becomes the center of an entirely new conversation. Yet before we can evaluate any claim, we must do something that many sensational videos skip entirely. We must understand the mathematics. What exactly is a yojana? How long is a nimeṣa? Which historical definitions are being used? How are these values converted into modern units like kilometers and seconds? And most importantly, when we perform the calculation ourselves without shortcuts or exaggeration, what number do we actually get? The answer to that question is where the mystery truly begins. In the next chapter, we'll step away from history and into mathematics, carefully examining the ancient units one by one to see whether the famous calculation really does produce a value remarkably close to the modern speed of light, or whether the story is more complicated than it first appears. Every extraordinary claim rests on one simple question. Can the numbers actually be verified? Stories can spread across the internet in a matter of hours. A single image with bold text can convince millions of people. But mathematics doesn't care about opinions. Numbers either work or they don't. So before we ask whether the Vedas, or more precisely Sāyaṇa's commentary, describes the speed of light, we must first understand the ancient units themselves, because everything depends on two Sanskrit words, yojana and nimeṣa. Without understanding these units, the famous calculation becomes meaningless. Let's begin with the yojana. In ancient India, the yojana was primarily a unit of distance. It appears in numerous Sanskrit texts, including works on astronomy, geography, epics, and traditional cosmology. Kings measured journeys in yojanas. Pilgrims estimated long distances using yojanas. Astronomers described celestial motions with yojanas. It was one of the most important large-scale units of measurement in classical Indian literature. But here's where things become complicated. Unlike the modern kilometre or mile, the exact length of a yojana was not always the same. Different texts describe it differently. Some traditions define it through a chain of smaller units. Others assign slightly different values depending on context. Even among historians today, there isn't complete agreement on one universal conversion. Some estimates place a yojana at around 8 kilometers. Others suggest values closer to 13 kilometers. Some historical reconstructions fall somewhere in between. This matters enormously, because changing the length of a single yojana changes the final result dramatically. Imagine measuring the distance between two cities. If one person says a mile equals 1 kilometer, while another uses the correct definition, they'll reach completely different conclusions. The same challenge exists here. Now, let's examine the second unit, the nimeṣa. Traditionally, the word itself is associated with the blink of an eye. Ancient Indian scholars often used everyday experiences to describe units of time. A blink, a breath, the movement of the sun, the phases of the moon. These became natural ways to organize time long before mechanical clocks existed. However, just like the yojana, the nimeṣa was defined differently in different texts. Some later astronomical and philosophical works describe a hierarchy of time units, where many nimeṣas combine into larger intervals. Using one commonly cited traditional system, scholars estimate that a nimeṣa is approximately 0.213 seconds. Half a nimeṣa, therefore, becomes roughly 0.1065 seconds. Notice something important. We now have two quantities, a distance and a time. That's exactly what's needed to calculate speed. This is why the statement in Sāyaṇa's commentary attracts so much attention. The commentary says the sun traverses 2,202 yojanas in half a nimeṣa. If we choose one traditional conversion for the yojana and one traditional conversion for the nimeṣa, we can perform the calculation ourselves. No mystery, no hidden equations, just arithmetic. Let's use one of the commonly cited traditional values. Suppose 1 yojana is approximately 9.1 miles, or about 14.6 kilometers. Multiply that by 2,202. The distance becomes a little over 32,000 kilometers. Now divide that distance by 0.1065 seconds. The resulting speed is approximately 300,000 kilometers per second. Pause for a moment. Modern physics tells us that the speed of light in a vacuum is approximately 299,792 kilometers per second. The two numbers are undeniably close enough that people around the world have asked the same question. How is this possible? Could medieval scholars really have known something so astonishing, or is there another explanation? Before jumping to conclusions, let's slow down, because this is exactly where careful historical investigation becomes essential. The apparent agreement depends on the particular values chosen for the yojana and the nimeṣa. If different historical definitions are used, the calculated speed changes, sometimes significantly. This isn't a minor technical detail. It's one of the central issues in the debate. Supporters argue that the traditional values producing the close match are legitimate and appear in respected Sanskrit sources. Critics respond that these units varied across history, making it difficult to claim a single definitive conversion. Both observations are true. Ancient measurement systems often evolved over centuries. This wasn't unique to India. Even the length of a foot varied across civilizations. The mile changed throughout history. Weights and measures differed between kingdoms, regions, and eras. Standardization is largely a modern achievement. Another important point is often overlooked. Even if the calculation produces a number close to the speed of light, mathematics alone cannot tell us what the original statement intended to describe. Imagine finding an old manuscript stating that a bird travels a certain distance in a certain time. If the calculation happens to equal the speed of sound, does that prove the author was measuring sound? Not necessarily. Context matters just as much as numbers. What was being described? What did the surrounding text mean? How did scholars of that era understand the statement? These questions are just as important as the calculation itself. History is never solved by arithmetic alone. Yet there is something undeniably remarkable about this numerical coincidence, or possible insight, depending on one's perspective. It forces us to think carefully. It reminds us that ancient scholars were capable of sophisticated mathematics and precise systems of measurement. Indian mathematicians developed advanced numerical methods centuries before many parts of the world. Indian astronomers carefully observed planetary motion. Scholars calculated eclipses with impressive accuracy. Complex systems of geometry were used in altar construction and ritual design. These achievements are well documented and widely recognized. Understanding that broader intellectual tradition helps explain why a statement like this captures so much attention. It emerges from a civilization deeply interested in mathematics, astronomy, language, and the structure of the cosmos. Still, one question remains, even if the numbers line up. Was the statement actually referring to light, or was it describing something entirely different? That question cannot be answered by calculation alone. For that, we must return to the original Sanskrit text itself. Words matter, context matters, meaning matters. And in the next chapter, we'll examine the famous passage more closely, exploring what it says, what it doesn't say, and why the interpretation of a single sentence has divided scholars for generations. So far, we've examined the history, we've met the scholar, we've broken down the mathematics, and we've seen why the famous calculation has captured the imagination of millions. But numbers alone can never tell the whole story. To understand this mystery, we must return to where it all began. Not with modern calculations, not with YouTube videos, not with internet debates, but with the Sanskrit text itself. Because in ancient literature, context is everything. A single sentence taken out of context can mean something completely different from what its author intended. That's why historians insist on reading ancient texts carefully, line by line, rather than relying on isolated quotations. The passage at the center of this debate appears in Sāyaṇa's commentary on Rig Veda 1.50, a hymn dedicated to the sun. The hymn itself is one of praise. It celebrates the sun as the bringer of light, warmth, order, and life. To the Vedic poets, the sun was not merely an object in the sky, it was the visible force that marked the passing of time. It revealed the world after darkness. It sustained crops, guided travelers, and inspired countless reflections on the nature of existence. Many ancient civilizations viewed the sun in a similar way. The Egyptians honored Ra, the Greeks revered Helios, the Romans worshipped Sol. Across cultures, the sun represented life itself. The Vedic tradition was no exception. Its hymns are rich with symbolism, poetry, and philosophical insight. This is important because the language of the Vedas is rarely technical in the modern scientific sense. It is poetic, layered, often metaphorical. The same verse may carry ritual, philosophical, and natural meanings simultaneously. That makes interpretation both fascinating and challenging. While commenting on this hymn, Sāyaṇa includes a statement that has become world famous. In translation, it is often rendered approximately as "it is remembered that the sun traverses 2,202 yojanas in half a nimeṣa." Notice something immediately. The statement says the sun, not light, not photons, not electromagnetic radiation. It refers to the sun. This raises the first major question. When Sāyaṇa wrote these words, what exactly did he mean? Was he describing the motion of the sun across the heavens? Was he referring to sunlight spreading across the world? Was he repeating a traditional saying whose original context had already been forgotten? Or was he making an observation that later generations would connect with the speed of light? The text itself does not explicitly answer these questions, and that silence is precisely why scholars continue to debate it. Supporters of the speed of light interpretation argue that the apparent motion of the sun cannot literally reach such an enormous speed. Therefore, they suggest the statement is more naturally understood as referring to the propagation of sunlight. From this perspective, the numerical value becomes remarkably intriguing. Critics, however, respond differently. They point out that ancient texts often use grand numbers symbolically or cosmologically. They argue that interpreting the passage as a measurement of light may project modern scientific ideas onto a medieval commentary. They also note that the concept of the speed of light, as understood in modern physics, did not exist in the same conceptual framework during Sāyaṇa's time. These are important objections. History demands that we consider them seriously. Another fascinating detail often goes unnoticed. Sāyaṇa does not present this statement as a discovery he personally made. Instead, he introduces it as something already remembered in tradition. That wording suggests he is citing an earlier source or a traditional saying familiar to scholars of his time. Unfortunately, the exact origin of that traditional statement remains uncertain. No surviving text has been universally accepted as its definitive source. This mystery has only deepened public fascination. If Sāyaṇa was quoting an older tradition, how old was that tradition? Did it originate centuries before him? Or was it part of medieval scholarly culture? No one knows with certainty. And when certainty disappears, speculation often rushes in to fill the gap. This is where careful scholarship becomes essential. It is tempting to jump directly from a mysterious number to an extraordinary conclusion, but history rarely rewards shortcuts. The greatest historians ask difficult questions. Where did the statement come from? How was it understood by contemporaries? How do other commentators interpret it? Are there parallel passages elsewhere? What do the surrounding verses suggest? These questions matter because ancient texts cannot be understood in isolation. Language evolves, meanings change, symbols acquire new interpretations across centuries. Even today, a sentence written hundreds of years ago can be misunderstood if we ignore its historical setting. The same challenge exists with Sanskrit literature. One word may carry several meanings depending on context. A poetic expression may later be interpreted literally. A ritual description may also have philosophical significance. This richness is one reason Sanskrit has fascinated linguists for generations. As we explore this mystery, it's worth remembering something remarkable. Long before modern observatories, ancient Indian scholars carefully observed the skies. They tracked the movements of the sun and moon. They predicted eclipses. They studied planetary cycles. They developed sophisticated calendars. Their interest in celestial phenomena was genuine and extensive. Whether or not this particular statement refers to the speed of light, it emerged from a civilization deeply engaged with astronomy and mathematics. That broader context should never be overlooked. At the same time, appreciating ancient achievements does not require exaggerating them. Real accomplishments are impressive enough on their own. India's documented contributions to mathematics, astronomy, grammar, logic, and philosophy have influenced civilizations for centuries. Recognizing those achievements strengthens historical understanding rather than diminishing it. Perhaps the most fascinating aspect of this entire debate is that both supporters and skeptics agree on one point. The statement is unusual. Its numerical value deserves examination. Where they differ is in how that examination should be interpreted. Does the closeness to the modern speed of light reveal forgotten scientific knowledge, or does it illustrate how easily modern readers can discover familiar patterns in ancient texts? That question remains open, and perhaps that's why this story continues to inspire curiosity. Because mysteries invite investigation. They challenge assumptions. They force us to examine evidence rather than rely on headlines. In the next chapter, we'll move beyond the verse itself and explore something even more surprising. Long before Europe entered the scientific revolution, Indian astronomers were developing sophisticated mathematical models of the heavens. What exactly did they know? How accurate were their observations? And could that broader scientific tradition provide clues about the famous statement in Sāyaṇa's commentary? To answer those questions, we must step into the remarkable world of ancient Indian astronomy, a world that continues to astonish historians even today. Long before telescopes pointed toward distant galaxies, long before satellites orbited the Earth, long before the laws of gravity and electromagnetism were written into textbooks, humanity had only one laboratory, the night sky. Every civilization looked upward. The stars became calendars, the moon became a clock, the sun became the measure of seasons. But among the great astronomical traditions of the ancient world, one stands out for its remarkable continuity and mathematical sophistication: the tradition of ancient India. To understand why the famous statement in Sāyaṇa's commentary attracts so much attention, we first need to appreciate the intellectual world from which it emerged. Because contrary to a common misconception, astronomy in ancient India was not limited to mythology or ritual. It was also a science of observation. For centuries, Indian scholars carefully tracked celestial movements with extraordinary patience. Night after night, year after year, generation after generation. They observed the changing positions of stars, they recorded the paths of planets, they calculated lunar cycles, they predicted eclipses, and they developed mathematical systems capable of describing the heavens with impressive accuracy. This wasn't accidental. Ancient Indian society depended heavily on astronomy. Agriculture required accurate knowledge of seasons. Religious ceremonies followed precise calendars. Navigation relied on the sky. Kings consulted astronomers before important events. Understanding the heavens was both practical and philosophical. One of the earliest branches of this tradition became known as Jyotisa, often translated as the science of celestial observation. Its earliest surviving texts focused largely on calendars and ritual timing, but over the centuries, Indian astronomy became increasingly mathematical. Scholars began asking deeper questions. How long is a year? Why do eclipses occur? How do planets move? How can future celestial events be predicted? Answering these questions required something more than careful observation. It required mathematics. And mathematics became one of ancient India's greatest strengths. Centuries before much of Europe embraced advanced algebra, Indian mathematicians had already developed sophisticated numerical methods. The decimal place value system evolved in India. The concept of zero as a number found one of its most influential mathematical expressions here. These innovations transformed calculation forever. Without them, modern science, engineering, and computing would look very different. Astronomy benefited enormously from these mathematical advances. Perhaps no figure illustrates this better than Āryabhaṭa, the brilliant 5th century mathematician and astronomer. More than 800 years before Sāyaṇa wrote his famous commentary, Aryabhata produced calculations that amazed later generations. He estimated the length of the solar year with remarkable precision. He explained lunar and solar eclipses through the shadows of the earth and moon rather than supernatural causes. He argued that the apparent daily movement of the stars could be understood through the rotation of the earth itself, a profoundly insightful idea for his time. His work demonstrated something important. Ancient Indian scholars were not merely preserving tradition, they were actively investigating nature. Generations after Āryabhata, another extraordinary scholar emerged, Brahmagupta. His writings expanded mathematics and astronomy even further. He developed methods for solving equations. He refined astronomical calculations. His influence eventually spread beyond India into the Islamic world and later into Europe through translations. Knowledge crossed cultures. Ideas travelled farther than armies. Then came Bhaskara II, whose 12th century works revealed astonishing mathematical sophistication. His writings explored planetary motion, geometry, arithmetic, and algebra with remarkable clarity. Modern historians often marvel at how advanced many of these methods were. Taken together, these scholars reveal something undeniable. Ancient India possessed one of the world's great scientific traditions. Its achievements in mathematics and astronomy are not matters of speculation. They are well documented in surviving texts studied by historians across the globe. This broader context is essential, because when people hear the claim that an ancient Indian text contains a number close to the speed of light, they sometimes imagine an isolated civilization making impossible discoveries. The historical reality is more interesting. India was home to generations of careful observers, gifted mathematicians, and innovative astronomers. That doesn't automatically prove the speed of light interpretation, but it does show that sophisticated numerical thinking was entirely consistent with the intellectual environment of the time. Still, we must be careful. Great achievements in one area do not automatically validate every modern claim made about ancient texts. History doesn't work that way. A civilization can excel in mathematics without having measured every physical constant known today. Likewise, recognizing uncertainty about one claim does not diminish its genuine accomplishments elsewhere. True scholarship celebrates verified achievements while remaining open but cautious about unresolved mysteries. This balanced approach is what makes history so fascinating. It allows us to admire ancient brilliance without abandoning critical thinking. As we continue our investigation, another question naturally arises. If Indian astronomers possessed such advanced mathematical knowledge, how did they actually make their observations? After all, they had no telescopes, no electronic clocks, no lasers, no satellites. Yet somehow they calculated eclipses, tracked planetary motions, and constructed remarkably accurate calendars. How? The answer lies in an extraordinary combination of patience, geometry, naked eye observation, and mathematical reasoning. Ancient observatories often relied on carefully aligned structures. Simple instruments measured shadows cast by the sun. Angles were recorded. Seasonal changes were tracked over decades. Patterns slowly emerged. Unlike modern science, which often depends on powerful machines, ancient astronomy depended primarily on time. Lots of time. A single generation might begin a set of observations. The next generation would continue them, and the generation after that would refine them further. Knowledge accumulated slowly, like drops filling a great river. Perhaps that is one of the most inspiring lessons from the ancient world. They understood that truth was rarely discovered overnight. It was earned through patience, through careful observation, through disciplined calculation, through the willingness to question and refine earlier ideas. That spirit of inquiry is timeless, whether we are studying the movements of planets or trying to understand a mysterious sentence written hundreds of years ago. The same principles apply. Observe carefully, calculate honestly, question respectfully, and follow the evidence wherever it leads. Because in the next chapter, our investigation takes an unexpected turn. We'll leave medieval India behind and travel into the modern age, where physicists finally measured the speed of light with extraordinary precision. Only then can we answer the question that has driven this entire documentary: just how close is the famous Vedic number to the value accepted by modern science? And is that similarity extraordinary enough to change the way we view history? For thousands of years, humanity looked at light without ever asking one question: how fast does it travel? The sunrise seemed instantaneous. Lightning flashed across the sky in an instant. A torch illuminated a dark room the moment it was lit. Naked eye, light appeared to move infinitely fast. Even some of the greatest philosophers of the ancient world believed exactly that. Aristotle, whose influence shaped scientific thinking for centuries, argued that light travelled instantaneously. For nearly 2,000 years, few had reason to doubt him. After all, how could anyone possibly measure something so unimaginably fast? Without electronics, without precision clocks, without lasers, it seemed impossible. Then, in the 17th century, everything changed. A Danish astronomer named Ole Rømer was studying one of Jupiter's moons. His goal had nothing to do with light. He simply wanted to predict the timing of eclipses involving Io, one of Jupiter's largest satellites. But something strange kept happening. Sometimes the eclipses occurred exactly when expected. Other times they arrived several minutes late. At first, this inconsistency puzzled astronomers. Was Jupiter behaving unpredictably? Were the calculations wrong, or was something else happening? Rømer noticed a fascinating pattern. When Earth was moving farther away from Jupiter in its orbit around the Sun, the eclipses appeared later than expected. When Earth was moving closer, they appeared earlier. The moons weren't changing their motion. The distance between Earth and Jupiter was changing. And if light required time to travel across that extra distance, the observations suddenly made perfect sense. In 1676, Rømer reached a revolutionary conclusion. Light did not travel instantaneously. It had a finite speed. This was one of the greatest scientific breakthroughs in history. For the first time, humanity realized that light itself obeyed measurable laws. Although Römer's estimate wasn't perfectly accurate by modern standards, he had opened an entirely new field of investigation. Over the following centuries, scientists refined the measurement again and again. In the 19th century, the French physicist Hippolyte Fizeau designed an ingenious experiment using a rapidly spinning toothed wheel. A beam of light passed through the wheel, travelled several kilometres to a distant mirror, reflected back, and attempted to pass through the same gap. As the wheel rotated faster and faster, the returning light was blocked by the next tooth. By carefully measuring the wheel's speed, Fizeau calculated the speed of light directly on Earth. It was an extraordinary achievement. Soon afterward, another French scientist, Léon Foucault, improved the method using rotating mirrors. His measurements became even more accurate. Each new experiment reduced uncertainty. Each new generation of scientists came closer to the true value. Then came one of the greatest physicists of all time, James Clerk Maxwell. In the 1860s, Maxwell unified electricity and magnetism into a single mathematical theory. While working through his equations, he discovered something astonishing. The equations predicted waves travelling at a specific speed. When he calculated that speed, it matched the measured speed of light almost exactly. This led to an extraordinary realization. Light itself is an electromagnetic wave. Suddenly, light was no longer merely something we could see. It became part of the fundamental structure of the universe. The 20th century brought even greater discoveries. Albert Einstein placed the speed of light at the very heart of modern physics. According to his theory of special relativity, the speed of light in a vacuum is not just another number. It is a universal constant. No object carrying information can travel faster. Space and time themselves behave differently because this speed remains constant for every observer. What had begun as a mystery involving Jupiter's moons became one of the pillars of modern science. Today, the speed of light in a vacuum is known with extraordinary precision. Its accepted value is 299,792,458 meters per second, or approximately 299,792 kilometers per second. This number is so fundamental that modern scientists actually use it to define the meter itself. In other words, instead of measuring the speed of light using the meter, the modern definition of the meter is based on the speed of light. That's how confident science has become in this constant. Now, let's return to the statement we've been investigating. Using one commonly cited set of traditional conversions, Sāyaṇa's famous value works out to approximately 300,000 kilometers per second. Compare the two figures. Modern value, 299,792 kilometers per second. Traditional calculation, roughly 300,000 kilometers per second. The difference is surprisingly small, just a fraction of 1%. No wonder the comparison spread around the world. No wonder it sparked books, documentaries, debates, and endless online discussions. At first glance, the resemblance is astonishing, but responsible investigation requires one more question. Is numerical closeness enough to establish historical knowledge? Not necessarily. Scientists deal with similar situations all the time. Two measurements may agree closely, yet they may arise for entirely different reasons. Sometimes a result is genuine. Sometimes it is coincidence. Sometimes hidden assumptions influence the calculation. History demands the same level of caution. We must distinguish between an impressive numerical match and proof of what an ancient author intended. This is where the discussion becomes most interesting. Supporters argue that such a close agreement is too remarkable to dismiss lightly. Critics respond that the calculation depends on selecting specific historical values for ancient units and interpreting the passage in a particular way. Both perspectives deserve careful consideration, because extraordinary questions deserve careful answers. What cannot be denied, however, is that this comparison has inspired millions of people to look more deeply into ancient Indian mathematics, astronomy, and literature. Perhaps that is one of its greatest contributions. It encourages curiosity. It encourages investigation. It reminds us that ancient civilizations deserve to be studied seriously, rather than dismissed or romanticized. Whether the famous number ultimately represents forgotten scientific knowledge, an intriguing coincidence, or something in between remains an open question for historians, Sanskrit scholars, and historians of science. And that is exactly where our journey leads next, because mathematics is only one piece of the puzzle. The next question is even more important. What do modern historians, Sanskrit experts, and physicists actually think about this claim? Do they see compelling evidence? Or do they see a misunderstanding created by reading modern science into an ancient text? In the next chapter, we'll examine the strongest arguments from both sides, not to declare a winner, but to understand why this remarkable mystery continues to fascinate the world centuries after Sāyaṇa first put pen to palm leaf. By now, we've uncovered something undeniably fascinating. A medieval Sanskrit commentary contains a numerical statement that, when converted, using one commonly cited set of traditional units, produces a value remarkably close to the modern speed of light. That much is true. But history doesn't end with a calculation. In fact, that's where the real debate begins. Because whenever an ancient text appears to anticipate modern science, scholars ask a simple but essential question. What did the author actually mean? Not, what do we wish the author meant? Not, what would make the best headline? But, what does the evidence support? This is where opinions begin to diverge. On one side are researchers, historians of Indian science, and enthusiasts who believe the numerical agreement deserves serious attention. They argue that dismissing the calculation as mere coincidence is too easy. After all, ancient India produced extraordinary mathematicians and astronomers. Scholars like Āryabhaṭa, Brahmagupta, and Bhaskara II demonstrated remarkable mathematical sophistication centuries before the European scientific revolution. Supporters point to this broader intellectual tradition as evidence that advanced numerical reasoning certainly existed. They also note that Sāyaṇa did not invent the statement. He introduced it as something remembered from tradition. If he was quoting an older source, they ask, could that tradition preserve knowledge whose origins are much earlier than the 14th century? Some even suggest that countless manuscripts have been lost over the centuries, libraries burned, palm leaf manuscripts decayed, wars destroyed centers of learning. If only a fraction of ancient literature has survived, is it possible that important scientific works disappeared with it? It is a question worth considering. History is full of lost knowledge. The Library of Alexandria is only the most famous example. Across the world, civilizations have lost texts through fire, flood, invasion, and simple decay. So the possibility that ancient ideas vanished over time cannot be dismissed outright. Yet possibility is not proof, and this is where the other side of the debate begins. Many historians, Sanskrit scholars, and historians of science urge caution, not because they underestimate ancient India, quite the opposite. Most readily acknowledge the immense achievements of Indian mathematics, astronomy, linguistics, and philosophy. Their concern lies elsewhere. They ask whether the evidence actually supports the specific conclusion being drawn. Their first objection concerns language. The statement mentions the sun, not light. Nothing in the passage explicitly identifies the number as the speed of light in the modern physical sense. Supporters argue that the motion of sunlight is implied. Critics respond that implication is not the same as explicit statement. A second concern involves measurement. As we've already seen, the exact values of the yojana and the nimeṣa varied across different historical traditions. Choosing one particular set of conversions produces a remarkably close result. Choosing another may not. Historians therefore ask whether the selected values reflect what Sāyaṇa himself intended, or whether they were chosen because they happened to produce an impressive modern comparison. This is an important methodological question. Whenever historians translate ancient measurements into modern units, they must justify every step carefully. Otherwise, even honest calculations can become misleading. A third concern involves historical context. The modern concept of the speed of light belongs to physics. It emerged through centuries of experimentation involving telescopes, rotating mirrors, electromagnetic theory, and eventually Einstein's theory of relativity. Critics argue that we should avoid assuming ancient authors were discussing the same concept unless the surrounding evidence clearly indicates it. This approach has a name among historians. It is often called presentism, the tendency to interpret the past through modern ideas rather than understanding it on its own terms. Presentism can create fascinating stories, but it can also distort history. Imagine discovering a medieval text describing invisible forces between objects. Would that automatically mean the author understood gravity exactly as Isaac Newton did? Probably not. The words may sound familiar, but context matters. The same principle applies here. Perhaps the most balanced position is also the most intellectually demanding. It accepts two ideas at the same time. First, ancient India unquestionably possessed one of the world's greatest traditions of mathematics and astronomy. Its documented achievements deserve recognition without exaggeration. Second, the specific claim that Sāyaṇa's commentary intentionally records the speed of light remains debated because the historical evidence allows more than one interpretation. Holding both ideas together requires intellectual honesty. It avoids two extremes. One extreme dismisses ancient civilizations as incapable of sophisticated thought. History clearly disproves that. The other extreme treats every numerical coincidence as proof of advanced modern science. History also cautions against that. Real scholarship lives between those extremes. It welcomes surprising discoveries, but it also demands strong evidence. Perhaps that's why this mystery has endured for decades. Neither side has produced evidence so overwhelming that the discussion simply ends. Supporters continue examining traditional sources. Historians continue analyzing language and context. Sanskrit scholars continue debating interpretation. And the conversation evolves as new research appears. In many ways, this is exactly how knowledge advances. not through certainty, but through careful questioning, through respectful disagreement, through the willingness to test ideas rather than defend them at all costs. Ironically, that spirit of inquiry is something both ancient philosophers and modern scientists would probably admire, because science itself is not a collection of permanent answers. It is a method, a way of asking questions, testing explanations, accepting evidence, changing conclusions when better evidence appears. Perhaps that is the greatest lesson hidden within this debate. The true value of the famous number may not lie in proving that ancient scholars knew the speed of light. Its greatest value may be something even more important. It encourages millions of people to open ancient texts, to learn Sanskrit history, to explore Indian mathematics, to investigate astronomy, to ask difficult questions instead of accepting easy answers. And in doing so, it bridges thousands of years of human curiosity. But one question still remains. If this famous passage continues to divide experts, are there other examples where ancient Indian texts seem to contain knowledge that appears surprisingly modern? Were these isolated coincidences, or part of a much larger intellectual tradition? In the next chapter, we'll step beyond the speed of light and explore several remarkable ideas found in ancient Indian mathematics, astronomy, and philosophy, discoveries that historians widely recognize, alongside others that continue to inspire debate even today. The mystery surrounding the famous number has led many people to ask an even bigger question. Was this an isolated coincidence? Or was ancient India genuinely far ahead of its time? To answer that honestly, we need to separate two very different kinds of claims. The first consists of ideas that are well documented, supported by surviving manuscripts, and widely accepted by historians. The second consists of interpretations that remain actively debated. Where the evidence is incomplete or open to multiple readings, the distinction matters. Because when genuine achievements are mixed together with speculative claims, both suffer. The documented accomplishments deserve recognition. The unresolved mysteries deserve careful investigation. Let's begin with what historians overwhelmingly agree upon. One of the greatest gifts ancient India gave the world was something so ordinary today that most of us rarely think about it: the number 0. Imagine trying to perform modern mathematics without 0. No calculators, no computers, no digital technology, no place value numbering system. Virtually every aspect of modern science depends upon it. While many ancient civilizations used symbols to represent the absence of quantity, Indian mathematicians developed 0 into a true mathematical number that could participate in calculations. This seemingly simple idea revolutionized mathematics forever. From India, it traveled through the Islamic world into Europe, where it became one of the foundations of modern science. Without it, physics itself would look very different. Then there was the decimal place value system. Today, writing a number like 5,432 seems effortless. Each digit has a value determined by its position: thousands, hundreds, tens, ones. We learn this as children, but this elegant system was one of humanity's greatest mathematical inventions. Roman numerals, by comparison, become cumbersome when handling large calculations. The Indian numeral system transformed arithmetic into something faster, more flexible, and vastly more powerful. Again, its influence eventually spread across the world. Ancient Indian astronomy also achieved remarkable precision. Scholars carefully measured the length of the solar year. Although different astronomical texts produced slightly different values, several estimates came impressively close to modern measurements. This required generations of careful observation, no satellites, no telescopes, just mathematics, geometry, and extraordinary patience. Indian astronomers also understood the true cause of eclipses. Rather than viewing them solely through mythological symbolism, works such as those of Āryabhaṭa explained lunar and solar eclipses as the result of shadows cast by the Earth and the Moon. This represented an important scientific insight. Observation had begun replacing speculation. Mathematics had begun explaining nature. Another extraordinary achievement was trigonometry. Today, engineers, physicists, architects, and astronomers rely on trigonometric functions every day. Ancient Indian mathematicians developed sophisticated tables of signs that greatly improved astronomical calculations. Their methods later influenced scholars far beyond India's borders. The story doesn't end there. Indian scholars made lasting contributions to algebra. They developed techniques for solving equations. They explored negative numbers. They investigated infinite series centuries before similar ideas emerged in Europe. Some historians have even noted striking similarities between later European mathematical developments and earlier Indian work, though the exact pathways of transmission remain subjects of ongoing research. Language itself became a science. Perhaps nowhere is this more astonishing than in the work of Panini. Living more than 2,000 years ago, he produced one of the most sophisticated grammatical systems ever created. His analysis of Sanskrit was so precise that modern linguists continue to study it today. Some computer scientists have even drawn inspiration from its rule-based structure when discussing formal languages and computation. These achievements are not legends. They are preserved in surviving texts. They have been studied by historians. They have influenced civilizations across continents. Recognizing them requires no exaggeration. Reality is impressive enough. Yet alongside these firmly established accomplishments exist a number of fascinating claims that remain debated. The speed of light is one example. Others involve descriptions of aircraft, advanced medicine, cosmology, or interpretations of symbolic passages as scientific discoveries. Some of these ideas may contain kernels of historical truth. Others may reflect metaphor rather than technology. Still others remain impossible to verify because the evidence is incomplete. Responsible scholarship treats each claim individually. It neither dismisses everything nor accepts everything. It asks the same question every time. What does the evidence actually show? This approach may seem less dramatic than sensational headlines, but in the long run it produces something far more valuable: trust. Because genuine history does not need embellishment. The documented achievements of ancient India already place it among the world's greatest centers of intellectual development. That legacy stands securely on its own foundation. Perhaps this realization changes the way we should approach the famous number in Sāyaṇa's commentary. Instead of asking, did the Vedas secretly contain all of modern physics? Perhaps a better question is, what kind of civilization produced scholars capable of preserving sophisticated mathematics, astronomy, philosophy, linguistics, and observational science over thousands of years? That question has a remarkable answer. It reveals a culture deeply committed to learning, to memorization, to debate, to observation, to disciplined reasoning, to preserving knowledge across generations. Whether discussing ritual, philosophy, language, mathematics, or astronomy, the underlying spirit remained the same. Seek understanding. Question carefully. Preserve what is learned. Pass it forward. In many ways, that spirit still defines science today. Modern laboratories may use particle accelerators instead of shadow sticks, supercomputers instead of palm leaf manuscripts, space telescopes instead of naked eye observations, but the essential human impulse has never changed. We still look upward, we still measure, we still calculate, we still wonder, and perhaps that continuity is the greatest bridge between the ancient world and our own. The tools have changed. The questions remain remarkably familiar. As our journey continues, one final mystery demands our attention. If the famous calculation truly fascinated so many people, why did it become widely known only in recent times? For centuries, Sāyaṇa's commentary remained largely within scholarly circles. Then suddenly, it exploded across books, documentaries, lectures, and the internet. How did a single sentence from a medieval Sanskrit commentary become one of the most debated historical claims in the modern world? That story is every bit as fascinating as the number itself, and it begins not in ancient India, but in the age of global communication, for nearly 600 years. The statement in Sāyaṇa's commentary remained largely where it had always been, inside Sanskrit manuscripts, studied by scholars, discussed within traditional circles, known to those who devoted their lives to Vedic literature. It was not front-page news. It was not the subject of documentaries. It certainly wasn't being debated by millions of people across the internet. So what changed? How did one sentence from a 14th century commentary become one of the most talked about historical mysteries of the modern age? The answer begins with a revolution that transformed the entire world: the printing press. For centuries, Indian knowledge had been preserved primarily through handwritten manuscripts, palm leaves, birch bark, carefully copied texts. Each manuscript required enormous effort to reproduce. Errors had to be corrected manually. Copies were limited. Knowledge spread slowly. Then came printing. Suddenly, texts that had once existed in only a handful of manuscripts could reach thousands of readers. Ancient works began crossing borders more easily than ever before. During the 18th and 19th centuries, European scholars developed a growing interest in Sanskrit literature. Linguists, historians, and philosophers traveled to India or worked with manuscripts that had reached libraries across Europe. They encountered something unexpected: an ancient language of extraordinary complexity, texts preserving philosophical ideas unlike anything they had previously studied, sophisticated systems of grammar, mathematical works, astronomical treatises, and the Vedas. Scholars began translating these ancient texts into English, German, French, and other European languages. For the first time, people outside traditional Sanskrit learning could read them. This marked the beginning of modern Indology, the academic study of Indian history, languages, and culture. Translation, however, introduced a new challenge. Every translation is also an interpretation. A Sanskrit word may carry several meanings. A poetic phrase may resist exact rendering. A cultural concept may have no perfect equivalent in another language. Even today, translators often disagree over the best way to express ancient passages. Sāyaṇa's famous statement was no exception. As more scholars examined his commentary, attention slowly turned toward the mysterious numerical value. For many decades, it remained an interesting historical curiosity. Then something unexpected happened. The 20th century witnessed astonishing advances in science. Physicists measured the speed of light with incredible precision. Einstein's theories transformed our understanding of space and time. Public fascination with science reached new heights. People began looking back into ancient civilizations with fresh eyes. Could earlier cultures have understood more than we realized? This question inspired researchers across many fields. Some revisited Egyptian mathematics, others explored Babylonian astronomy, still others investigated Greek philosophy, and naturally, many turned toward India's vast scientific heritage. At some point, someone noticed something extraordinary. Using one commonly cited set of traditional conversions, Sāyaṇa's numerical statement produced a value astonishingly close to the modern speed of light. That comparison spread quickly. Books mentioned it, lectures discussed it, newspapers occasionally referenced it. Later, television documentaries introduced it to wider audiences. Then came the internet, and everything changed. Information that once required months of library research could now reach millions of people in seconds. A fascinating claim no longer remained inside academic journals. It became a viral headline. Social media accelerated the process even further. Short videos compressed centuries of history into 60 seconds. Images displayed dramatic comparisons between ancient Sanskrit verses and modern physics. Some presentations encouraged careful investigation. Others simplified the story into bold declarations. The Vedas discovered the speed of light, the mystery science cannot explain, the ancient secret hidden for thousands of years. These headlines attracted enormous attention. After all, humans love mysteries. We love stories that challenge accepted history. We enjoy discovering surprising connections between the ancient world and modern science. But rapid communication has one disadvantage. Complex ideas often become simplified. Nuance disappears. Historical debates become absolute conclusions. Questions become certainties. And careful scholarship struggles to compete with dramatic headlines. This isn't unique to the Vedas. The same pattern appears across history. Ancient Egypt, the pyramids, Stonehenge, the Maya. Every great civilization eventually becomes surrounded by extraordinary claims. Some prove true, some remain unresolved, some collapse under closer examination. The challenge is learning how to distinguish among them. This is where critical thinking becomes invaluable. Rather than asking, "Do I like this claim?" or "Does this support my beliefs?" a better question is, what evidence supports it? Where does the information come from? Can the original source be examined? How do specialists interpret it? Are alternative explanations possible? These questions protect us from both blind skepticism and blind acceptance. Interestingly, the modern discussion surrounding Sāyaṇa's commentary has produced one unexpected benefit. It has encouraged renewed interest in ancient Indian scholarship. Many people who first encountered the speed of light claim eventually discovered something even more remarkable: the authentic history of Indian mathematics, the achievements of Āryabhaṭa, the genius of Panini, the innovations of Brahmagupta, the astronomical brilliance of Bhaskara. Even if someone initially arrived searching for a sensational mystery, they often left with a deeper appreciation for India's documented intellectual legacy. In that sense, curiosity became a doorway to genuine learning. Perhaps that is the greatest irony of this entire story. Whether or not the famous calculation ultimately represents an intentional measurement of light, it has inspired countless people to study history more seriously, to read original texts, to question assumptions, to appreciate civilizations often overlooked in mainstream narratives, and perhaps that is exactly what great historical mysteries should do, not provide instant answers, but awaken curiosity. Because curiosity is where every scientific discovery begins, every philosophical insight, every mathematical breakthrough, every journey toward understanding. Our investigation, however, is not quite finished. There remains one final question. After examining the history, the mathematics, the language, the astronomy, and the scholarly debate, what conclusion should we actually draw? Should the famous number be celebrated as evidence of forgotten scientific brilliance? Should it be dismissed as coincidence? Or is the truth somewhere between those extremes? In the final chapter, we'll bring together every piece of evidence we've explored and discover why the greatest lesson hidden within this mystery may have nothing to do with the speed of light at all, but with humanity's timeless pursuit of knowledge. We've travelled across thousands of years, from the hymns of the Rig Veda to the commentaries of Sāyaṇa, from ancient observatories to modern laboratories. We've explored mathematics, history, astronomy, language, and one mysterious number that continues to spark debate around the world. Now comes the most important question of all. What should we take away from this story? Is the famous calculation undeniable proof that ancient India measured the speed of light? The honest answer is, history cannot say that with certainty. The numerical comparison is undeniably intriguing. Using one commonly cited set of traditional conversions, the value attributed to Sāyaṇa's commentary comes remarkably close to the modern speed of light. That similarity deserves attention. It deserves investigation. It deserves thoughtful discussion. But history also reminds us that the statement itself does not explicitly describe the modern scientific concept of the speed of light, and scholars continue to debate how it should be interpreted, recognizing that uncertainty is not a weakness, it is the foundation of honest scholarship, because real knowledge grows stronger when it can withstand difficult questions. At the same time, another conclusion is equally undeniable. Ancient India was home to one of humanity's greatest intellectual traditions. That is not speculation. It is history. Generation after generation, Indian scholars observed the heavens with extraordinary care. They refined mathematical techniques. They developed systems of logic. They analyzed language with astonishing precision. They preserved knowledge through an oral tradition unlike anything else in the ancient world. Think about that achievement for a moment. For centuries before printing presses, before digital storage, before libraries as we know them, entire collections of sacred texts were memorized with such precision that even a misplaced syllable could be detected. Modern researchers have often marveled at the sophistication of these methods. Knowledge wasn't simply written down, it was lived, practiced, recited, protected, passed from one generation to the next. That alone is one of civilization's greatest accomplishments. The story of the famous number also teaches us another important lesson. Curiosity is timeless. Whether we are reading a Vedic hymn, studying the movements of Jupiter, building a telescope, or launching a spacecraft, the human desire to understand the universe remains unchanged. Thousands of years separate ancient astronomers from modern physicists. Yet they shared the same sky. They watched the same sunrise. They measured the same seasons. They wondered about the same stars. The tools changed. The questions endured. Perhaps that continuity is more profound than any single numerical coincidence. Too often history is presented as a competition. Which civilization discovered something first? Who deserves the credit? Who was more advanced? But knowledge has never belonged to one culture alone. It grows through observation, through dialogue, through preservation, through generations building upon the work of those who came before. Indian mathematics influenced scholars across Asia and the Middle East. Arabic translations carried knowledge westward. European scientists expanded upon earlier discoveries. Modern physics stands upon foundations laid by countless civilizations working across thousands of years. Science is not the achievement of one nation. It is humanity's shared inheritance. The same is true for wisdom. The Vedas continue to inspire millions, not merely because of mysterious numbers. They ask enduring questions. What is the nature of reality? How should human beings live? What connects us to the universe? What is truth? These questions remain as relevant today as they were thousands of years ago. Modern science excels at explaining how the universe works. Ancient, philosophical traditions often explored why human beings seek understanding in the first place. The two approaches need not compete. They can complement one another. Science provides measurement. Philosophy provides reflection. History provides context. Together, they offer a richer understanding than any one discipline alone. Perhaps that is the greatest lesson hidden within this famous debate, whether the number represents forgotten scientific insight, an extraordinary coincidence, or something in between. It has inspired millions to look beyond headlines, to read ancient texts, to study history, to appreciate the brilliance of civilizations that came before us. And that curiosity has value regardless of where one ultimately stands on the question, because every generation inherits two responsibilities: to preserve knowledge and to question it. The ancient scholars who memorized the Vedas fulfilled the first responsibility. The historians, linguists, mathematicians, and scientists who continue investigating these texts fulfill the second. Both are essential. Without preservation, knowledge disappears. Without questioning, knowledge stagnates. Progress requires both. As we conclude this journey, perhaps it's worth returning to the image with which we began. Imagine an ancient scholar sitting beneath the open sky. No telescope, no computer, no laboratory, only careful observation, patient calculation, and an endless sense of wonder. Now imagine a modern scientist standing beside a space telescope orbiting Earth. Different technology, different methods, yet driven by the same desire to understand the universe, separated by centuries, united by curiosity. That may be the real legacy of the Vedas, not necessarily that they contained every scientific answer we seek today, but that they emerged from a civilization unafraid to ask profound questions about the cosmos. Questions that inspired observation, questions that inspired mathematics, questions that inspired philosophy, questions that continue to inspire us today. So, did the Vedas really know the speed of light? The evidence invites curiosity, the history invites humility, and the mystery remains open for thoughtful minds to explore. Perhaps the most remarkable discovery was never the number itself. Perhaps it was the realization that across thousands of years, humanity has always looked toward the light, seeking not only to measure it, but to understand what it reveals about the universe and about ourselves. If this journey challenged what you thought you knew, let it be the beginning. rather than the end. Keep questioning, keep reading, keep exploring. Because the greatest discoveries are often made not by those who already have the answers, but by those who never stop asking the questions. Before you decide whether the famous number proves anything, pause for a moment. Imagine that tomorrow archaeologists uncover a sealed library beneath the sands of India. Inside are thousands of perfectly preserved manuscripts, books that no historian has ever seen, treatises on astronomy, mathematics, philosophy, medicine. Would that discovery surprise you? Probably not, because history has taught us something important. Much of the ancient world has already been lost. Palm leaf manuscripts decay, libraries burn, kingdoms fall, languages evolve, entire schools of thought disappear. When we study ancient history, we're not reading everything our ancestors wrote. We're reading only what survived. Think about that. The books sitting in your home today may still exist 100 years from now. Digital files are copied endlessly across the world. Cloud servers preserve information almost instantly. Ancient civilizations had no such luxury. Every manuscript had to be copied by hand. One page at a time, one line at a time, one generation at a time. If a manuscript wasn't copied, it slowly vanished. Humidity destroyed it. Insects consumed it. Time erased it. Historians estimate that countless works from the ancient world have disappeared forever. This isn't unique to India. Ancient Greece lost hundreds of philosophical works. Egypt lost enormous collections of temple records. China lost classics during wars and political upheavals. The famous Library of Alexandria became a symbol of humanity's lost knowledge. India experienced similar losses. Great universities such as Nalanda and Vikramashla once attracted students from across Asia. They housed enormous collections of manuscripts covering philosophy, medicine, astronomy, mathematics, grammar, and logic. Travelers described libraries containing vast numbers of texts. Many of those collections no longer exist. Wars, fire, neglect, and time itself took their toll. No historian can say exactly what disappeared, and that uncertainty is important. Notice what it does not prove. It does not prove that every modern scientific theory was hidden in those lost books. But it also reminds us not to assume that everything ancient scholars knew has survived. There is a profound difference between possibility and proof. Good historians respect that difference. Sometimes the most honest answer is simply, we don't know. In today's world, many people are uncomfortable with those words. We prefer certainty, definite conclusions, simple headlines. But history rarely offers that luxury. The deeper we investigate the past, the more we encounter unanswered questions. Where exactly did Sāyaṇa's famous statement originate? We don't know. Was he quoting an even older source? Possibly. Can that older source be identified with certainty? Not yet. Did ancient scholars intentionally calculate the speed of light? The surviving evidence does not allow historians to answer that confidently, and perhaps that's okay, because uncertainty is not failure. Uncertainty is an invitation. It motivates further research, it encourages better translations, it inspires archaeologists to continue excavating. It drives linguists to compare manuscripts. It pushes historians to question long-held assumptions. Without uncertainty, there would be no discovery. Consider modern science itself. Scientists rarely begin with certainty. They begin with observations. Then they form hypotheses. They test those hypotheses. Some survive, others fail. Knowledge advances one careful step at a time. History follows the same path, each newly discovered inscription, each recovered manuscript, each archaeological excavation adds another piece to an enormous puzzle. Sometimes those pieces confirm what we already believed. Sometimes they overturn centuries of assumptions. Imagine if someone had told scholars 200 years ago that an ancient Indian mathematician had developed sophisticated algebra centuries before Europe. Many would have doubted it. Today, the evidence is well established. History changed because new evidence emerged. The lesson is clear. Never underestimate the past, but never exaggerate it either. Respect the evidence. Follow where it leads. One of the greatest strengths of ancient Indian scholarship was precisely this balance between preservation and inquiry. Teachers preserved sacred traditions with astonishing precision. At the same time, mathematicians refined calculations, astronomers improved observations, philosophers debated competing ideas. Knowledge was not frozen, it evolved. That spirit remains deeply relevant today. Perhaps the greatest tribute we can pay to the ancient scholars is not blind admiration. It is continuing their search for understanding. Reading carefully, questioning respectfully, learning patiently. Because every civilization leaves behind mysteries, some are eventually solved, others remain unsolved for centuries. The speed of light debate may ultimately join either category. Future discoveries could clarify its origin. New manuscript evidence could reshape our understanding. Or historians may conclude that the mystery arose from later interpretation. At this moment, we simply do not know. And that honest uncertainty makes the story even more fascinating. It reminds us that history is not a finished book, it is a conversation. Every generation asks new questions. Every generation uncovers forgotten evidence. Every generation sees the past through fresh eyes. Perhaps one day another palm leaf manuscript will emerge from a forgotten temple library. Perhaps an overlooked commentary already sitting in an archive will reveal new context. Perhaps advances in digital manuscript analysis will uncover connections invisible to earlier scholars. History still has many surprises waiting. As we approach the end of this journey, one final thought deserves reflection. Maybe we've been asking the wrong question all along. Instead of asking, did the Vedas predict modern science? Perhaps we should ask, what can modern humanity learn from the way ancient civilizations pursued knowledge? That question has an answer no historian disputes. They observed patiently. They preserved carefully. They debated openly. They valued learning across generations. And above all, they never stopped looking toward the heavens with curiosity. In our final chapter, we'll step back from the debate entirely and explore why that timeless curiosity may be the greatest legacy the Vedic tradition has left for the modern world. We've reached the end of our journey, but perhaps this isn't an ending at all. Perhaps it's a beginning of looking at history differently, a beginning of asking better questions, a beginning of appreciating the past, not as a collection of myths or miracles, but as a record of humanity's relentless search for understanding. Throughout this documentary, we've followed one mysterious statement from a medieval commentary on the Rig Veda. We've explored the mathematics behind it. We've examined the ancient units of measurement. We've looked at the remarkable closeness between one traditional calculation and the modern speed of light. We've also listened carefully to the arguments from historians, Sanskrit scholars, and scientists who remind us that the interpretation remains debated. Some viewers may walk away convinced that the ancient tradition preserved extraordinary scientific insight. Others may conclude that the numerical similarity is an intriguing coincidence shaped by later interpretation, and many may find themselves somewhere in between. That diversity of opinion is not a weakness. It is exactly how genuine intellectual inquiry works. The greatest discoveries in history often begin with disagreement. Questions come first, answers come later, sometimes centuries later. What matters is not which side we personally prefer. What matters is whether we are willing to follow the evidence honestly, even when it challenges our expectations. If this investigation has taught us anything, it is that ancient civilizations deserve far more respect than they are often given. For generations, history books focused heavily on only a few regions of the world. Yet the deeper historians looked, the clearer the picture became. Knowledge flourished in many places: in India, in Greece, in China, in Mesopotamia, in Egypt, in the Islamic world. Each civilization contributed something unique to humanity's shared understanding of reality. Ancient India contributed profoundly through mathematics, astronomy, linguistics, philosophy, and systems of knowledge that continue to influence the world today. Those contributions do not need exaggeration. They are already extraordinary. The invention and development of the decimal place value system, the mathematical treatment of zero, sophisticated astronomical calculations, remarkable grammatical analysis, deep philosophical inquiry. These achievements changed the course of human history. Perhaps the most inspiring lesson, however, isn't found in any single discovery. It's found in the attitude behind them. The ancient scholars who composed hymns, calculated eclipses, debated philosophy, and preserved knowledge across generations, shared something with every great scientist who came after them: curiosity. They looked at the world and refused to accept ignorance as the final answer. When they saw the stars, they didn't merely admire them. They counted them, measured them, predicted their movements. When they observed language, they didn't simply speak it. They analyzed its structure with astonishing precision. When they encountered difficult questions about existence, they didn't avoid them. They explored them through reason, dialogue, and reflection. That spirit still defines the best of humanity. It is the same spirit that led Galileo to point a telescope toward Jupiter, the same spirit that inspired Newton to ask why apples fall, the same spirit that drove Einstein to imagine riding alongside a beam of light. Curiosity connects them all, thousands of years apart. Different cultures, different beliefs, different tools, one shared desire to understand. Perhaps that is why the story of Sāyaṇa's mysterious number continues to fascinate us. Not because everyone agrees on what it means, but because it reminds us that the pursuit of knowledge has always crossed generations. Every civilization inherits questions from those who came before. Some questions receive answers, others remain open, and some inspire entirely new fields of study. This mystery belongs to that third category. Whether future historians ultimately confirm, reinterpret, or reject the modern speed-of-light comparison, the conversation itself has already accomplished something valuable. It has encouraged millions of people to open ancient texts, to study Sanskrit, to learn about Indian mathematics, to explore astronomy, to appreciate history with greater depth, and perhaps, most importantly, to question. In an age dominated by instant information, questioning has become more important than ever. The internet can spread knowledge faster than any civilization in history, but it can also spread misunderstandings just as quickly. That places a responsibility on all of us, not merely to consume information, but to examine it, to trace ideas back to their sources, to compare evidence, to distinguish between established history and fascinating possibility. This isn't skepticism for its own sake. It is respect. Respect for truth. Respect for the scholars who devoted their lives to preserving ancient knowledge. Respect for scientists who carefully test ideas before accepting them. And respect for the civilizations whose achievements deserve to be understood accurately. Imagine standing beneath the night sky, just as countless generations have done before us. The stars appear timeless. The sun rises as it always has. Light still travels across the universe, illuminating worlds we have yet to discover. Somewhere, a child looks upward for the first time and wonders what those distant lights really are. That child asks the same question ancient sages once asked, the same question astronomers ask today, the same question future explorers will continue asking centuries from now. How does this universe work? That question is the true inheritance of humanity, not a single equation, not one mysterious number, but an endless desire to understand reality. And perhaps that is the greatest legacy of the Vedic tradition. Not that it necessarily contained every answer, but that it inspired people to keep searching, to observe carefully, to think deeply, to preserve knowledge, and to pass curiosity from one generation to the next. So the next time you hear someone say, "The Vedas knew the speed of light," or "That's impossible," remember what we've discovered together. The truth is richer than either slogan. It is a story of remarkable scholarship, ancient mathematics, astronomical brilliance, historical mystery, and, above all, the timeless human search for light. Not only the light that travels across space, but the light of knowledge that illuminates every generation willing to seek it. Thank you for joining this journey, and remember, the greatest discoveries are rarely the ones that end a conversation. They are the ones that inspire the next question. If you've stayed with this journey until now, you've probably realized something important. This story was never just about one number. It was never just about whether an ancient commentary happened to produce a value close to the speed of light. Because even if that mystery were solved tomorrow, the larger question would remain: how did a civilization thousands of years old develop such an extraordinary tradition of mathematics, astronomy, philosophy, and linguistic precision? That question deserves just as much attention. History often celebrates the discoveries of the modern age: the telescope, the steam engine, electricity, computers, spaceflight. These inventions transformed the world. But every breakthrough stands on foundations built by earlier generations. No civilization begins from nothing. Knowledge is cumulative. Every generation inherits ideas, improves them, and passes them forward. Ancient India was one of the great builders of that foundation. Its scholars were asking profound questions at a time when much of the world was still developing written traditions. How should numbers be represented? Can language itself be described through rules? How do planets move? How can eclipses be predicted? What is the relationship between observation and reality? These weren't casual curiosities. They became lifelong pursuits. Perhaps the most remarkable aspect of Vedic and post-Vedic scholarship wasn't any single discovery. It was the culture of learning itself. Students often spent years living with their teachers, Knowledge wasn't downloaded in an afternoon. It was absorbed slowly, repeated, questioned, memorized, debated, perfected. Imagine spending a decade mastering a single branch of knowledge. Today, information is measured in gigabytes. Back then, it was measured in discipline. One forgotten verse could take weeks to memorize correctly. One mistake in pronunciation could completely alter a sacred recitation. This demanded extraordinary concentration. It also created minds trained to notice patterns with incredible precision. Perhaps that explains why Indian scholarship flourished across so many fields simultaneously: mathematics, astronomy, medicine, grammar, logic, music, architecture, philosophy. Each discipline strengthened the others. Astronomy required mathematics. Mathematics benefited from logical reasoning. Logic depended upon language. Language was refined through grammar. Knowledge became interconnected rather than isolated. Modern universities often divide subjects into separate departments. Ancient scholars frequently saw them as parts of one greater search for truth. That holistic approach continues to inspire researchers even today. It reminds us that understanding reality rarely comes from looking at only one piece of the puzzle. Sometimes the most important discoveries occur where different fields meet. Consider modern physics. Albert Einstein wasn't merely solving mathematical equations. He combined mathematics, philosophy, observation, and imagination. Likewise, ancient Indian scholars often approached knowledge as an integrated whole. Perhaps that's one reason their writings continue to attract interest centuries later. Not because every statement predicts modern science, but because they encourage a way of thinking, a willingness to ask enormous questions, questions about consciousness, time, infinity, the universe, reality itself. Those questions never become outdated. Technology changes. Human curiosity does not. Even today, scientists still struggle with mysteries that ancient philosophers contemplated in very different ways. What is the nature of time? Is the universe eternal? How did everything begin? What is consciousness? What is reality beyond perception? Modern science investigates these questions through experiments and mathematics. Ancient traditions often explored them through philosophy and observation. Different methods, similar curiosity. This doesn't mean the answers are identical. It means the search itself has always united humanity. Perhaps that's why discussions like the speed of light debate become so emotionally powerful. They touch something deeper than history. They challenge our assumptions about the past. For generations, many people assumed ancient civilizations possessed only primitive knowledge. Yet archaeology has repeatedly challenged that belief. Sophisticated engineering, advanced metallurgy, complex urban planning, accurate calendars, remarkable mathematics. Every decade seems to uncover new reasons to respect our ancestors. That doesn't mean every extraordinary claim is automatically true. It simply reminds us not to underestimate the people who came before us. History has humbled us many times before. It will almost certainly do so again. Maybe another forgotten manuscript still waits inside an old temple archive. Maybe another archaeological discovery will reshape what we know. Maybe future technology will help historians recover damaged texts once considered unreadable. The past still has secrets. That much is certain, and perhaps that is the greatest reason to remain curious, not because curiosity guarantees extraordinary answers, but because it keeps us searching. The Vedic scholars understood something timeless. Knowledge is never complete. Every answer creates another question. Every discovery reveals another mystery. That principle still drives modern science. No physicist believes all the mysteries of the universe have been solved. No historian believes every ancient manuscript has been discovered. No astronomer believes every galaxy has been mapped. Human knowledge continues expanding, and so does our awareness of how much remains unknown. Maybe that's the true message hidden within this entire journey. Whether we are reading a Vedic hymn, studying a medieval commentary, or observing distant galaxies through a space telescope, the goal remains the same: to move a little closer to understanding. Not by abandoning evidence, not by rejecting tradition, but by allowing both to guide us toward deeper questions. Because in the end, the speed of light may not be the most important thing the Vedas inspire us to think about. The most important thing may simply be this: never stop looking, never stop questioning, never stop learning, for the greatest distance humanity has ever traveled is not measured in kilometers. It is measured in understanding, and that journey is far from over. There is an old saying among historians: the past is never as simple as we imagine it. The deeper we investigate history, the more complicated it becomes. Simple stories slowly disappear. Easy answers begin to fade, and in their place emerges something far more valuable: understanding. When this journey began, we asked a seemingly straightforward question. Did the Vedas know the speed of light? After thousands of words, ancient texts, mathematical calculations, historical debates, and centuries of scholarship, you may have noticed something unexpected. The answer isn't a simple yes. It isn't a simple no. It's an invitation to think more deeply, because history rarely rewards certainty. It rewards curiosity. Throughout this documentary, we've encountered two extremes. On one side are those who dismiss every ancient civilization as primitive. To them, sophisticated knowledge could only belong to the modern world. Anything impressive found in an ancient text must be coincidence, exaggeration, or myth. History has repeatedly shown that this attitude is mistaken. Again and again, archaeology has revealed remarkable achievements once thought impossible: cities with advanced drainage systems, precise astronomical observatories, complex mathematical texts, ingenious engineering, civilizations that understood far more than earlier generations of historians had imagined. Underestimating the past has become one of history's oldest mistakes. But there is another extreme. Some believe every mysterious verse hides modern science. Every symbolic passage becomes a technological blueprint. Every poetic description becomes evidence of forgotten machines. This approach creates exciting stories, but history asks us to be more careful. Ancient texts deserve respect. That includes respecting what they actually say, not only what we hope they might say. The greatest scholars are those who resist both temptations. They neither underestimate ancient civilizations nor exaggerate them. Instead, they allow evidence to lead the way. That balance is more difficult than it sounds. It requires patience, humility, and the willingness to change one's mind. Science works this way. History works this way. Truth itself demands this approach. Imagine standing in an enormous library. One shelf contains books we have read. Another shelf contains books we have not yet opened. But somewhere beyond those shelves are books that no longer exist. Books destroyed centuries ago. Books still buried underground. Books waiting to be discovered. Our understanding of history is built from the first shelf. But we must never forget the existence of the others. This is why historians speak with caution, not because they lack curiosity, but because they understand how incomplete the surviving evidence truly is. The Vedic tradition illustrates this beautifully. Thousands of verses survived through one of the world's most extraordinary oral traditions. Later commentators preserved additional layers of interpretation. Astronomers expanded mathematical knowledge. Philosophers explored profound questions about reality. Each generation inherited something precious. Each generation added something new. Knowledge was never static. It evolved. The same process continues today. Modern science is often presented as the opposite of ancient wisdom. In reality, they share something fundamental. Both depend on observation, both depend on careful reasoning, both require the courage to admit uncertainty. One uses particle accelerators, the other used the naked eye. One records data electronically, the other memorized verses with astonishing precision. Different methods, one shared goal, understanding reality. Perhaps this realization changes the way we should see the relationship between ancient knowledge and modern science. Instead of competitors, they become chapters of the same human story. Every civilization contributes a few pages. None writes the entire book. The Egyptians mastered monumental architecture. The Babylonians refined astronomy. The Greeks advanced philosophy and geometry. Chinese scholars transformed engineering, navigation, and medicine. Indian thinkers revolutionized mathematics, linguistics, and astronomy. The Islamic Golden Age preserved and expanded knowledge across multiple civilizations. Europe's scientific revolution accelerated experimental science. Modern researchers build upon all of them. Knowledge has always crossed borders. Ideas travel farther than empires. A mathematical concept born in one civilization may transform another centuries later. A manuscript translated into a new language may inspire discoveries unimaginable to its original author. Perhaps the greatest mistake we can make is believing wisdom belongs exclusively to one culture. History teaches the opposite. Human progress has always been collaborative. The mystery surrounding Sāyaṇa's famous number reminds us of this beautifully. Whether it ultimately proves to be an astonishing scientific insight, an intriguing coincidence, or something historians have not yet fully understood. It has already achieved something remarkable. It has inspired conversation across continents. Physicists have examined it. Historians have debated it. Sanskrit scholars have translated it. Students have become curious about ancient India. Readers have opened the Rig Veda for the first time. That alone gives the mystery lasting significance. Sometimes a question changes the world more than its answer. Think about the greatest scientific breakthroughs. Isaac Newton asked why objects fall. Albert Einstein wondered what it would be like to travel alongside a beam of light. Modern cosmologists ask what existed before the observable universe. Every revolution in knowledge begins with curiosity. The Vedic tradition encourages that same habit of mind. Observe, reflect, question, seek. Those principles remain timeless. As we prepare to conclude this documentary, there is one final thought worth carrying with you. Imagine two people standing beneath the same night sky. One lived 3,000 years ago, the other lives today. Both look upward, both feel wonder, both ask questions. The stars shining above them are the same. The universe they seek to understand is the same. Only the tools have changed. That realization is deeply humbling, because despite all our technological progress, humanity is still searching. still learning, still discovering, and perhaps we always will be. In our final chapter, we'll leave behind debates, calculations, and controversies. Instead, we'll reflect on why stories like this continue to captivate millions, and why the greatest light the Vedas may offer is not a physical measurement at all, but a reminder that the pursuit of knowledge is itself one of humanity's most sacred journeys. As we come to the end of this journey, let's return to the question that brought us here. Did the Vedas really know the speed of light? After examining the history, the mathematics, the Sanskrit commentary, the ancient units, the achievements of Indian astronomy, and the ongoing scholarly debate, the most honest answer is surprisingly simple. The mystery remains unresolved. The numerical comparison is remarkable. The historical context is fascinating. The intellectual tradition behind it is undeniable, but the surviving evidence does not allow historians to state with certainty that the passage was intended as a measurement of the speed of light in the modern scientific sense. And perhaps that honesty makes the story even more powerful, because truth has never feared uncertainty. In fact, every great discovery in human history began with uncertainty. There was a time when humanity didn't know that Earth orbited the Sun, a time when no one understood why eclipses occurred, a time when gravity had no mathematical explanation, a time when the stars seemed fixed forever. Every answer we possess today was once a mystery. Every certainty was once a question. That is why history should never be viewed as a finished book. It is a living conversation. Each generation inherits what the previous generation discovered, then asks new questions, finds new evidence, corrects old mistakes, and passes a richer understanding to those who follow. The Vedas have participated in that conversation for thousands of years. Regardless of how one interprets the famous number, one fact stands beyond dispute. These texts have inspired generations of thinkers to ask profound questions. Questions about nature, about consciousness, about existence, about the universe itself. Few works in human history have remained intellectually influential for so long. That alone deserves admiration. Imagine the countless people who have recited these verses across the centuries: teachers, students, astronomers, philosophers, kings, poets, travelers. Each generation encountered the same words, yet each understood them through the lens of its own time. The same process continues today. Modern readers approach ancient texts carrying concepts like gravity, quantum mechanics, relativity, and cosmology. Naturally, we notice patterns our ancestors could never have described in the same language. Sometimes those patterns reveal genuine historical insights. Sometimes they reflect our own interpretations. Distinguishing between the two is one of the historian's greatest responsibilities. That responsibility belongs to all of us, especially in an age where information spreads faster than ever before. Today, a single headline can circle the planet within minutes. A dramatic claim can be repeated thousands of times before anyone checks the original source. This makes critical thinking more valuable than ever. Not cynical thinking, not dismissive thinking, critical thinking, the kind that asks, where did this claim come from? What does the original text actually say? What do experts agree on? Where does uncertainty remain? These questions don't weaken truth, they protect it. Throughout this documentary, we've tried to follow that principle, to appreciate the brilliance of ancient India without exaggeration, to recognize genuine historical achievements while acknowledging ongoing debates, to celebrate curiosity without sacrificing evidence. Perhaps that balance is the greatest tribute we can offer to the scholars of the past, because they, too, were seekers, whether composing hymns beneath open skies, calculating planetary positions, analyzing Sanskrit grammar, or preserving sacred knowledge through oral tradition. They dedicated their lives to understanding reality. That same pursuit continues today. Only the tools have changed. Modern observatories now peer billions of light years into deep space. Particle accelerators recreate conditions from the earliest moments of the universe. Quantum experiments explore realities invisible to human senses. Artificial intelligence analyzes patterns beyond ordinary perception. Yet despite these astonishing advances, the biggest questions remain. What existed before the universe? What is consciousness? Why does reality exist at all? How much remains unknown? The farther science advances, the larger the horizon of mystery becomes. Perhaps that is the greatest lesson hidden within this entire story. Knowledge does not eliminate wonder, it deepens it. The more we learn, the more extraordinary the universe appears. Maybe that's why civilizations separated by thousands of years still feel strangely connected. Ancient sages looked upward with wonder. Modern astronauts do the same from orbit. Ancient astronomers track the stars with the naked eye. Modern telescopes observe galaxies whose light began traveling long before humanity existed. Different instruments, the same curiosity, the same desire to understand, and perhaps the same sense of awe. So, if someone asks you, did the Vedas calculate the speed of light? You now know that the real story is far richer than a simple yes or no. You know about Sāyaṇa. You know about the traditional units. You know about the mathematical comparison. You know about the scholarly debate. And you know about the extraordinary achievements of ancient Indian mathematics and astronomy that are recognized around the world. Most importantly, you know that history is not a battlefield where we choose sides. It is a bridge connecting generations, cultures, ideas, and the endless human search for truth. Maybe that is the real light the Vedas have carried across the centuries, not merely the light of the sun, not merely a mysterious number, but the light of inquiry, the light of disciplined learning, the light of preserving knowledge so that future generations may ask even better questions. That light has travelled farther than any measurement could ever describe. It has crossed empires, languages, religions, and millennia. It reaches us today, and now it is our responsibility to carry it forward. So the next time you look toward the rising sun, remember that countless generations have stood where you stand, wondering, observing, calculating, questioning, seeking. Perhaps that shared pursuit is the greatest discovery of all, because civilizations rise and fall, empires fade, libraries may burn, manuscripts may disappear, but the human desire to understand the universe continues traveling through time like light itself, endlessly. Thank you for watching. If this journey sparked your curiosity, continue exploring. Read the original sources, study history, ask difficult questions, and never stop searching, because the universe still holds countless mysteries, and somewhere among them may be the next discovery waiting for someone curious enough to look.